Okay, well, maybe we should get started. Um, is this working?
Yeah, it's working.
Okay, and shall I start?
Yeah, you can start.
Okay, right. So yeah, I want to finish this section 5 on Bojanitson's paper, although I will leave a gap, unfortunately, which I only found out in preparing. I mean, it's probably something minor, but anyway, we finished last time with this proposition where I did the proof a little fast, maybe, but you should be able to fill in all the steps, I think. Right, so if you have a Hardy field and an element in it which is dominated by some power of x, then there is a unique twice differentiable germ satisfying this differential equation, and such that y minus any element in capital H is non-oscillating. And then, well, then we already know from this earlier theorem in the section that it generates, this little y generates a Hardy field, which in this case you can very explicitly indicate, namely the field generated by y and y prime, since y double is automatically in there and the higher derivatives then also. Right. So now the next, yeah, let me, so the next lemma, yeah, this is the last lemma before the theorem, 534, is again, right, well, so, yeah, so this in principle has nothing to do with Hardy field. This is just something about solutions of differential equations like that. Suppose you have, well, actually in this case, I'd like to assume that I actually have a function, not a germ. So this is a 1 times continuously differentiable function on the closed interval from a to, well, half closed up to plus infinity. And its derivative is at least is always greater than or equal to some fixed constant, right? Then for all y in C2a, if it solves the differential equation, y equals h, then y goes to infinity, or y is bigger than every real number. Let's explain what that means. Yt goes to plus infinity as t goes to plus infinity. Right. So this is just a purely fact, just a fact about asymptotics of ordinary differential equations of this. But we will need that. But I'm not mentioning any Hardy field there. So let me do the proof here. Well, first of all, we can of course increase A so that H is, let me see. Aha, this derivative is always bigger than or equal to a fixed positive constant, which means that it grows at least as fast as a linear function with positive slope. So ultimately it will be positive, right? So eventually h is ht greater than 0. So by increasing h, by increasing the number a, and of course restricting all the functions inside to the smaller interval, increasing a, we can arrange that, h is positive for all ht greater than 0 for all t going to a. Yeah, now it is enough to verify this for just one solution, right? Because you want to show that every solution goes to plus infinity, but the difference of two solutions is always a periodic function, yeah, linear combination of sine x and cosine x, which is bounded. And so it's enough to do this for the solution that is given by this integral that I wrote down earlier. So, so enough to verify y bigger than r for for the solution y in C2a given by this integral, yt equals, and here I may as well start the integration from a to t sine t minus s. Yeah, so we integrate with respect to s, but now we are going to write this as the integral. So I make a small change of variables. Instead of integrating from a to t, I integrate from 0 to t minus a. Oh, I forgot hs. ds. So then this turns into the integral from sine s ht minus s ds. Right, and any other solution differs from it by a bounded function. And now that will be, let Tn be a plus 2n pi. Yeah. And so for t greater than equal to Tn, we have that the integral from 0 to 2n pi of sine s ht minus s let me see, equals, well, you split it up into n sums, n is 0 up to, or j is 0 up to n minus 1, and the integral from 2j pi to j plus 1 pi of the same expression, sine s, ds h s minus t ds. Yeah, I mean, the condition t greater than equal to Tn is imposed here because we want to make sure that this hs minus, wait a minute, ht minus, this is t minus s, sorry. We want to make sure that h is defined for t minus s, for s between 0 and 2n pi. So that's why we impose this here, simply to make this well defined. Okay, and for j for j up to from 0 up to n minus 1, the jth integral here, the integral from 2j pi to j plus 1 pi sine s, it's g plus s ds is okay. Yeah, we again now do the change of variables where we integrate from 0 to 2 pi and the additive change of variables, sine s. So yeah, okay. Of course, if s runs from 2j pi to 2j plus 1 pi, that's the same as s running from 0 to 2 pi as far as the sine is concerned. And then here you get h of t minus 2j pi minus s ds is right. And now I split this up into the integral from 0 to pi and the integral from pi to 2 pi. And so what this amounts to is the integral from 0 to pi of sine s. Right, so from 0 to pi, the sign is positive, and then from pi to 2 pi, it's the negative. It runs through the same values, but the negative ones, the negatives of them. So this amounts to h of t minus 2j pi minus h t minus 2j plus 1 pi minus s ds. Right? In other words, this accounts for the integral from 0 to pi of this part, and and here you take the negative sign. This accounts for the integral from pi to 2 pi. Okay, and now this is greater than or equal to, this last thing you can see is greater than or equal to pi c. Let me see. Now let me see, did I already assume that h is always greater than or equal to c? Oh no, I didn't. I should have, let me see now, where am I? Oh yeah, no, that's okay. H prime is always, aha. Right, so here you have t minus 2j pi, here you have t minus 2j pi minus s minus pi. So so what can you say? H is increasing, and if h is increasing, did I say? Then this would have to be negative. That's a little. I'm a little confused. First of all, there is already a typo here, which there should be. Let me. H minus 2 minus s minus h 2 minus 2j plus 1 y minus s. Oh no, wait, yeah, this is yeah, no, this is bigger than that. Right. ds. Okay, this is bigger than that, but you can also, by the mean value theorem, estimate this to be greater than or equal to pi times times this constant, right? Because the derivative is greater than or equal to c, and right. So this is, and now you also oh, and now you integrate from sine, also the integral from sine s. Yeah, okay. So this is greater than or equal to the integral from 0 to pi of sine s times pi c ds, and this is again pi c. Yeah, yeah, cosine, that's right. This pi c is just a constant, and the integral from 0 to pi of sine s is cosine s between the bound 0 and pi, which is cosine of, wait a minute, why is, no, it must be true, but if I start to do the integral in my head, I get confused. So that's why it's better to just look at this and see, aha, this must be. Oh no, it's the integral of sine s, of course, is minus cosine s. That's what caused my confusion. I thought it was cosine s, but it's minus cosine s. Then it works. Yeah. Okay. Or is it? Wait a minute. Yes. No, but then wouldn't there then be a factor 2 here? A cosine of s with minus s between 0 and pi. The cosine is so that should be 2 pi c then. Do you agree? Okay. It's okay. Yes. Okay, and so therefore, since this, and now therefore the integral that I started with 0 to 2 n pi sine s, let me, 2 n pi of sine s h t minus s is ds is greater than to 2. Well, 2 n pi c, of course, it's for t greater, still for t greater than to tn, right? And for, well, of course, for t equals tn, this gives y of tn, the original from y given by this integral formula gives exactly, well, 2 n pi c. Right, and yeah, and okay, now you may wonder what happens between, if t is between tn and tn plus 1. Well, little can happen. Similar arguments, yeah, similar arguments, which I'm not going to spell out. Similar arguments with t between tn and tn plus 1. This inequality will still hold. Yeah. Get yt, right? It's just a little bit of extra integration, but over a piece where you can also make similar estimates, and 2 n pi. Okay, and that does it, because if t goes to infinity, then therefore yt goes equal to infinity as t. Right. Okay. Oh yeah, no, I said this was the last lemma before the theorem, but I forgot there is one more. And this does involve a Hardy assumption. 6, 5, 3, 5. Suppose now H is Hardian, so it lies in some Hardy field, a germ, and it dominates every power of X. Strictly dominate, right. And you have a solution of the usual differential equation, y and C2, y double plus y H, and then this y will also dominate all powers of X. So, yeah, in fact, if roughly speaking, if H is big enough, then the growth of the solution y is pretty similar. So then y dominates x to the power n for all n as well. Okay. Proof. Well, it will be an application of this lemma. So, well, first we can always make h positive by changing h to minus h and y to minus y, if necessary. So we can replacing h y by minus h minus y if necessary. Arrange that. Yeah, that of course doesn't make any difference for this domination relation, or for that one. Arrange h is positive. Okay, and then for if you now replace y, if you take yn equals y minus x to the power n, and hn, yeah, we now do a kind of additive change of the kind that we have seen before. If you take yn is y minus x to the n, then it will satisfy. And for y we have, yeah, we have yn double plus yn equals, well, hn, which is by definition h minus, well, a certain polynomial in x. It doesn't really matter which one, but let me write it down. Hn minus 1 minus okay, some polynomial in x, which you can easily come up with, right? And now this h, but look, since h dominates all the powers of x, this hn will still do that. Yeah. We still have. Yeah. Okay. Maybe it's a little bit confusing that here I use the same n as there. Maybe I should write here m here, and not to get confused with the m. Still, hm dominates all the powers of x to the x for all n, and so and hm prime, yeah, you see hm prime will also still, if hm dominates x to the n, then you well, then by the asymptotics in Hardy fields, hm prime will also still dominate all the powers of x. So hm prime dominates, well, all the derivatives of these powers, but that means really all powers, right? dominates x to the n for all n. In particular, we are in the situation that Hm satisfies the conditions in that lemma, right? Read Hm instead of H there, and you will see that all the conditions of the lemma are satisfied. That means that the the corresponding Ym has to go to infinity. Yeah? So Ym bigger than R for all m, for every m. Right, but Ym was y minus x to the m. So that means in particular that Ym is bigger than, so Ym dominates all the powers x to the, no, okay, y dominates all the powers for all m. Right, if Ym is positive for eventually, that means that, and this happens for every m, of course that means that y must dominate x to the n for all n. Okay, so yeah. Yeah, please interrupt or ask questions if something is not clear. But now we can actually state the main theorem that we were aiming for. And prove it. Yeah, the gap I alluded to in the beginning is somewhere else. It's not in this theorem. It's a real closed Hardy field. And h, little h and h. Now, of course, there are two possibilities. And this gives a kind of dichotomy. Then obviously, this is not the main conclusion. That obviously either you have the following, that's namely that f double plus f minus h is bounded, is dominated by some power of x, some n. Some n. That's one possibility. Or let me just, there's no reason to put parentheses around there. Two. Or this doesn't happen, and that means that for some f and for some f in h and n in and some n. And the other possibility is that this never happens. F double plus f minus h dominates all the powers for every f in h, all n. Right? It's clear that these are mutually exclusive possibilities, and one of them must be happen. And now the thing is that in case one, there is a unique solution that generates a Hardy field. So in case one, there is a unique y in C2 with, it solves the differential equation, generating the Hardy field over H. Yeah, a Hardy field extension of H or a Hardy field over H, that's just, you can actually say what it is, namely, if it does generate a Hardy field, then in fact it is just the field generated by y and y prime, right? Because y double is then automatically right. And in case 2, and that is the new phenomenon that we have to deal with. Every y in C2 with y double plus y equals h generates a Hardy field. And of course, there are continuum many. Once you always have a solution in C2 of this, and then if you add to the solution any linear combination of sin x and cosine x, in other words, solution of the homogeneous equation, you get another solution. Generates, and each of them generates a Hardy field extension over H, which again is as a field just generated by y and y prime. Right. So that is the main, in some sense, the main result of this section, and we can now quickly prove it. Yeah, of course. Yeah, in some sense, that proposition 533 is already a special case. Right. Yeah, let me. But I'm going to erase it. Or shall I start on? No, I think I'll keep it on there because I'll refer to it in the proof, and I'll erase another blackboard. Yeah, if anything, maybe the audience on that is on the Zoom might also. Are they able to ask questions?
Yes. Yes.
Oh, so yeah, feel free to interrupt me then. Okay. Right. Yeah, so that is the basic dichotomy, and I'll say a bit more about it later, but okay, proof. We've basically done all the work already, but if yeah, if you are in case 1, so if you have an F, if F and H and F double plus F minus H is dominated by x to the power n. Do I have to the power n? Then setting z equals y. Yeah, you just take the difference with f, y minus f. Oh, z plus f. Yeah, it's very Oh no, it's even, it is very difficult to get these things exactly right. Y equals Z plus F. Y equals Z plus F. Um, the ODE, Y double equals H. Transforms into C double with Z equals H minus F double plus F, which is dominated by X to the N here. In other words, right, instead of the original ODE, I make this change of unknowns, so to say, and look at this ODE, where now the right-hand side is dominated by a power of X. But then we had, yeah, then we can apply 533. Now apply 533, which tells you there is a unique solution that generates a Hardy field extension of H, right? Because the condition that Y minus F is non-oscillating for all F and H is simply equivalent to Y generating a Hardy field extension. So, right. So that takes care of the first claim that in case 1 there is unique Y generating a Hardy field. Now suppose we are in case 2. Yeah. Suppose we are in case 2. Okay, and Y in C2, Y double plus Y equals H. And I have to show that it does generate a Hardy field extension. Now for all, the point is we are simply going to show that Y minus any element in capital H is non-oscillating. And so then we know that it does generate a Hardy field extension. So for all F and H, because what 2 says, F double, well, Y minus, let me see. What is Y minus F? Double plus Y minus F. This is H minus F double plus F, which is still, which dominates X to the power N, right? Case 2 means that, yeah, this dominates all for all N. Okay, but now, now we can apply this lemma, right? We have a, wait a second now. Yeah, we have Y minus F, sorry. Y minus F satisfies exactly the kind of differential equation that here, except that the H here is H minus F double plus F. But the condition, the hypothesis is satisfied for H minus F double plus F. And so this, so by this lemma 535, Y minus F must also dominate x to the power n for all n. But in particular, this means that y minus f is non-oscillating, right? If y minus f would oscillate, which means it is zero for arbitrarily large arguments, then it could never dominate x to the power n. So y minus f is non-oscillating. And this is true for every f and h. So by the theorem we started out with, this section, 513, y generates a Hardy field over H. Right. And so any solution y of y double plus y is h will generate a Hardy field. But now I want to add remarks to this to see the true significance of 1 and 2, and why 2 is a kind of new phenomenon for Hardy fields. Okay. See. Okay, remarks. I guess this counts if theorem is what's the number of the theorem? If this is 535, that would have been 536. So the remarks would be 537. Remarks. Suppose we are in case 1. Suppose we are in case 1. Okay, so then the unique y, in C2 with y, it solves the differential equation that generates a Hardy field extension over H. Well, actually generates a Hardy field extension over any Hardy field extension of H. Actually generates. Yeah, it's a sort of, how shall I say, stable in the sense that even if you extend H, it will still generate a Hardy field over the extension. Actually generates a Hardy field extension of any Hardy field extension, Hardy fields H star containing H. Yeah? So even if you go to a bigger Hardy field, the same Y will still generate a Hardy field extension of it. Right. Why? Well, because over H star, you are still in case, yes. If you are in case 1, then you remain in case 1 if you go to a bigger Hardy field. And so there will be also a unique Y for that bigger Hardy field, but that Y that works for this bigger H, for H star, must be the same Y. right? Because that the Y that works for this bigger H star also generates a Hardy field over H. And therefore, yeah. Okay, if you think about that, this is all pretty obvious, I think. So, but now suppose we are in case 2. Suppose we are in case 2. Well, then, as I said, there will be in continuum many solutions of this differential equation, and each of them will generate a Hardy field, but any two of them cannot lie in the same Hardy field extension of H. So let's say, suppose we are in case 2. Then there are continuum many Y in C2 with Y double plus Y equals H, and each of them such Y generates a Hardy field H Y prime over H. But they are incompatible extensions. But suppose let Y1, Y2 be two such solutions. Yeah, they generate incompatible, let me say it this way, Hardy field extensions. Hardy field extensions. Y1 prime, Y2 prime. In which sense? Namely that no Hardy field containing H will contain both Y1 and Y2. Yeah, no Hardy field. No Hardy field H star containing H contains both Y1 and Y2, because the difference between Y1 and Y2 is a solution of the homogeneous equation Y double plus Y is 0, so it's a linear combination of sine and cosine. It's oscillating, in other words, so that can never be in a Hardy field. Yeah, so you can picture this, of course. You have H, Y1 prime, H, Y2 prime, and you cannot amalgamate them into a common Hardy field. And in fact, you have continuum many, right? So this is a kind of explanation for why there are so many maximal Hardy fields. Of course, each of these extends to a maximal Hardy field by its own, and there are 2 to the continuum many, because this kind of branching happens a lot. There are even 2 to the continuum many maximal Hardy fields. That's sort of the reason why, right? But there is, of course, I'm making here a tacit assumption, namely that case 2 actually occurs. I haven't proved that at all, and to my annoyance, I realized that the proof that case 2 actually occurs is in Bojanitson's paper is not, the proof is not completely, there is one line in the proof that I don't understand. And I only found this out yesterday when I was preparing for this. Oh yeah, but before I get to that, I want to make one remark. Actually, I don't think this this occurs any place that I know of. Well, maybe maybe it occurs in our big set of notes that we are writing now, but I'm not sure even then. But I think that these two Hardy field extensions are actually isomorphic. Plausible to me, plausible. But I'm not claiming it. I just like when you have I think it's very plausible that any two such extensions are isomorphic, right? So they are not compatible, but they are almost the same in this sense. And of course, when we talk about isomorphisms of Hardy fields, you have to say what structure you have in mind. Well, of course, the differential field structure and the ordering. Yeah, right. So as an ordered differential field, they are isomorphic over H, meaning that by an isomorphism, that is the identity on capital H. Yeah, so I haven't checked this, and not sure that anyone has checked this, but it should be true. Right. Sorry, can speak louder? Yeah. Yeah, something like that is probably should probably do the job. Well, have to be a little careful. H is a Hardy field. I'm not saying it is. Well, in some sense, yeah, okay. I mean, there are general theorems about extending H fields that you can probably also appeal to. But anyway, this is not, let's say, explicitly documented in the literature as far as I know, but it's very likely to be true. And if you can give me a precise reference, then I'd certainly be happy to hear. Right. Okay, but the gap I left is, does case 2 actually occur? And Bojanitsyn, of course, takes care of this. Yeah, now I think I can safely remove this one. Yeah. These lectures, I'm a little bit selfish because much of what I do is simply because I'm interested in all aspects of Hardy field, or many, understanding what Bojanitsyn has done, but it does not affect directly our own work on the model theory of Hardy fields. But still, this is I think these phenomena about Hardy fields are interesting. Let me see. Right. So this case two actually occur. Yes, and Bojanitson.
Excuse me.
Yes.
Yes, Fernando Sanz speaking.
Ah, yes. Mm-hmm.
Oh, yes. Can you hear me?
Yes, I can hear
okay.
you. Yeah.
No. I'm not so sure, but with Patrick Speisiger and Olivier Legal, we have studied linear differential equations in two variables. So your second order equation can be translated into a system of two linear equations.
Yeah.
Yeah. And we proved there that if the coefficients are in a Hardy field, then you have a dichotomy. Either all the solutions live in a Hardy field extension of the coefficients, or they are 2 by 2 linked, interlaced. And this dichotomy it's given just by looking if the Riccati equation associated to the system has a solution or not. And I have to check, but I think that this it's only to say that maybe your equation it's in the case where 2 by 2 solutions are interlaced, so it must enter in the case 2, but I have to check. I'm sorry, but just to say that.
Yes. Well, I know that there are I do know that for other linear differential equations, even even for y double plus fy is even for the homogeneous case, there are also important dichotomies. Different from that one, but in the same spirit, and where you also have incompatible extensions. So I know that this phenomenon occurs in other places, and there I do know the full proof. It's just that in this particular case, I'm basically just relying on a claim by Bojanitsan, but perhaps if we look at the paper that you quoted, maybe things will become clearer. Anyway, I'm just
okay. Yes. Thank you. Just to say that something reminds me.
Let me maybe you can send me the exact
reference.
Yes.
Of course. Yeah.
Okay. Good. Yeah. So by Bojanitsan. It happens for H, the real closure of x and e to the power x squared. Well, this is x and e to the power x squared. They generate a Hardy field by results that we did, and then the real closure, of course, is also a Hardy field, and y double plus y equals e to the power x squared. Right. So yes. Okay. So this is what he states as a result, and the proof. I could follow it except for 2 lines or 1 or 2 lines that are about algebraic functions, where uses terminology that I'm not totally familiar with. He talks about integral analytic functions. Maybe he meant entire analytic function, but anyway, if someone is interested in discussing this proof or seeing why it works, let me know. I mean, it's annoying to have this gap in my understanding. Right. You see, if you try this for a simple, trying it for say something that looks a little bit simpler, namely h's are x e to the power x and y double plus y equals, well, e to the power, I don't know, 3x or so. If you that doesn't work, you can easily come up with an element in this Hardy field such that the difference with e to the power, such that it's easy to come up with an element f in h such that f double plus f minus h is bounded by something small, like a doesn't work. So this is by the, yeah, I think this looks like the simplest kind of situation where this happens. Doesn't work. Also, yeah, it would be interesting to know whether the solutions of this generate O-minimal expansions of the real field. I think I've also stated this as a problem at some point. Right. I want to just like Bose-Nitson does, I want to formalize some aspects of this whole situation a little bit. Want to formalize some aspect. This situation. And I follow Bose-Nitson here in defining, so let H be a Hardy field. Then Bose-Nitson defines a bigger Hardy, well, in principle, a bigger Hardy field, namely those which can, those germs that can always be adjoint to any bigger Hardy field. Let me, yeah, but before I do that, let me introduce some terminology, which I should have done earlier, but call a germ, yeah, indefinitely differentiable, well, n times differentiable on a for every n ultimately. Call it Hardian over H, Hardian over H. Yeah. So before I had the terminology Hardian, but now I want to say over H if it generates a Hardy field extension. Yeah. Or you can also say if Y lies in some Hardy field H star containing H, or it generates a Hardy field extension of capital H. Yeah, Hardian over H, or also H Hardian. right. And before I just, the absolute version of this is simply Hardian, namely it lies in some Hardy field. Okay. Then right. Okay. So then E8 can be defined in a few equivalent ways. It's the intersection over all of all maximal Hardy fields extending H. And a maximal. Yeah, by John, there are maximal Hardy fields containing H, and maximal Hardy fields M containing H. Yeah, but an alternative, maybe more concrete description is simply all the Y's in that are H star Hardian for every H star containing Y equals H star Hardian. Yeah, so you can always join it to any bigger Hardy fields. They are really the core Hardian things over H. Hardian over is H Hardian for every H Hardy field. H star containing H. Yeah, I mean that these are things are the same are that's a little requires a little bit of thought, but not anything deep. It's just a matter of figuring out the definition. Yeah. Okay. So what do we know about EH? Yeah. What do we know? Yeah. So it's clear that Bose-Nitzan attaches a lot of significance to this construction. From the model theoretic point of view, it's a little strange, but still one has to pay attention to it. What do we know about the H? Well, of course, it's a Hardy field. The intersection of Hardy fields is a Hardy field, but we know that, for example, you can always add logs and exponentials and antiderivatives and all real numbers to any Hardy field. So that means that EH is going to be Liouville closed. So it is certainly pretty big. Let me first say, yeah, what do we know about it? Is a Hardy field. It is a Hardy field. Containing the original Hardy field H. Also, if you iterate this operation, capital E, doesn't change anything, right? EEH is H. Yeah. That's pretty clear. Right, so, well, first I want to mention some obvious things that are true about EH. It contains all the real numbers because a real number can always be adjoined to any Hardy field. You can always adjoin X to any Hardy field. And EA, as I already said, since you always can adjoin antiderivatives, any antiderivative, and exponential and logarithms, it's Liouville closed. So Liouville closed. But not only that, it also contains the cosine and the sine of any bounded elements. And cosine of y of h, sine of h must be it's for every h dominated by 1. In order it's a bounded element. I mean, this last statement is not a consequence of being Liouville closed and the other thing. So that's old stuff. But now we know, but now a negative thing, but the ODE y double plus 1 is e to the power x squared has no solution. In, well, E is simply Bose-Nitson's notation for EQ, right? In other words, the intersection of all maximal Hardy fields. Intersection of all maximal Hardy fields, or you could say it consists of elements that are adjoinable to every Hardy field. The core Hardian elements, so to say. Where do I? Yeah. Maximal Hardy fields is instead of all y, let's see, y is H Hardian for every Hardy field. So these are the most Hardian germs you can think of. For every Hardy field. Right. Right. But this very simple linear differential equation of order 2 has no solution in it. So that suggests that from a model theoretic point of view, this E might have a very complicated theory. I would not be surprised at all if it turned out to be undecidable. Right. But let me mention a few other facts just for your general education, so to say, about E. Right. So this is the smallest of those EHs. Because there are still interesting open questions about it. Right. Okay. Yeah. Other facts without. Well, and this is, if you first hear this, it sounds a little surprising, I think. At least it surprised me a bit. E is differentially algebraic over differentially algebraic. In the absolute sense, every element of E satisfies a polynomial differential equation over Q is differentially algebraic. Every Y in E satisfies an equation E Y prime up to yn 0 for some polynomial in y prime yn over Q, well, or over R, it doesn't really matter because yeah, whether I put here the reals or the rational numbers doesn't make any difference because the reals themselves are differentially algebraic over Q, since they are satisfy the differential equation y prime equals 0. So yeah, if you look at the definition of E as the intersection of all maximal Hardy fields, you would think that it doesn't seem that obvious that well, in fact, it is not obvious, but I will actually give a brief sketch of this fact. But as a consequence, which I will also, you can show that any Y in E is how shall I say, cannot be trans-exponential. Yeah? No, for every Y in E, there is an N such that Y is dominated by exp, the nth iterate of exp. Yeah, so x n times. It cannot. There are no trans-exponential elements in Y and E. That is simply a consequence of the fact that every such Y satisfies an algebraic differential equation. Now let me also okay. Yeah. So again, this is all without proof. I'm just mentioning, I think, facts that one should know when one deals with Hardy fields. Yes. A level. Yeah, level. At the moment, I wouldn't be able to say. I would suspect so, but I'm not at all sure whether this has been proved. It could be one more open problem. Yeah, so there are, and actually I want to mention a few open problems. Well, yeah, one other thing, which is I think very suggestive for some other stuff that I want to mention. E is closed under composition. Yeah, by which I mean if you have an element of E which is bigger than R, then you can always compose with it then E, if you compose any element in E with G or substitute G in it, you get back to E. But it's not known, they're open, whether is E closed under compositional inversion. Is E closed under compositional inversion. Right, so that's one open problem, and there is a good reason for mentioning this, because it's related, I think, to the next problem that I think is very interesting, whether it basically does E generate a O minimal expansion of the reals. More precisely, is E contained in the Hardy field of an O minimal expansion for some O minimal expansion R tilde of RL. Now, you see, if you have an O minimal expansion of the field of real numbers, then its Hardy field is closed under composition and is also closed under compositional inversion, right? So, well, E is closed under composition, but we don't know whether it's closed under compositional inversion. And if you could prove that, that would certainly be further evidence for a positive answer to the second question. I mean, it could even be that E equals the Hardy field of some O minimal expansion of the field of real numbers. And in fact, you could even ask, you could even make this more specific. There is one particular kind of expansion of RL, namely the Pfeffian closure, where so to make this more, I'm not sure if this is the, you have the field of real numbers. Now there is a general construction, the Pfeffian closure. Yeah, so Alex Wilkie started with that, and then as a general construction on Hardy fields, it was done by Patrick Spijsegger. Yeah, these Pfeffian functions seem to be very much like these the kind of functions that you can adjoin to any O minimal expansion of the reals and preserve O minimality. And so they so this suggests that maybe this would be a very strong positive answer to this question. Yeah, I don't know, maybe other people have already had these thought about this kind of thing, but right. Yeah, I want to sketch at least one business here, namely why is E differentially algebraic? Because that sounds, at first sight at least, rather surprising. But if you see the proof or the sketch of the proof I'll give, then you'll see why this is not not so outrageous at all. Okay, sketch for sketch of E being differentially algebraic. break. Okay, well, suppose you have a germ that is not differentially algebraic. Yeah. Suppose F is Hardian, but not differentially algebraic. Suppose F and C is Hardian, but not. Yeah, so it doesn't satisfy any differential equation like that. The thing is that then F can be perturbed a little bit, and it will still be Hardian, but not differentially algebraic. Okay, I can show, and again, this is in one of the papers of Bojanitsan. If phi is very small, let's say, so small, well, first of all, it should be a unit. In other words, ultimately it will be positive, or ultimately it will be negative. But it's so small that all its derivatives are dominated by 1 over En, or yeah, 1 over exp and x, right? The nth iterate of exp for all m and n, for all m and n. And so this is extremely small, right? It's not just that phi itself is smaller than all the 1 over the iterated exps, but all its derivatives as well. But the point is that such phis exist. Such phi exists. Phis. I'm not saying phi has to be Hardian. It's just such phi exists. Then, if you just add to f phi times the sign, so you add to f this small oscillating term, it will still be Hardian. It's still Hardian. It will still, and I'm sure that the f and f plus phi sine x will actually generate isomorphic Hardy fields. Right. So you just add this tiny oscillating term to f. It's still Hardian, but that means that they cannot lie f and and f plus phi times this tiny term phi times sine x cannot lie in a common Hardy field. Cannot lie in the same Hardy field. Because then the difference would lie in that Hardy field, and the difference is oscillating, yeah, since phi x oscillating. Right. So in a way, this is another phenomenon. This is another situation where you have this kind of branching. But here the branching already occurs over the ground field Q, so to say. So in other words, F cannot be in all maximal Hardy fields, because the maximal Hardy field that contains the second one, F plus V sine X, cannot contain F. So F is not in E. Yeah? So F. So this is, of course, a very indirect argument, so to say, that all elements in E have to be differentially algebraic. It doesn't. I mean, I have the feeling that our work, when I say our, I mean with Matthias Aschenbrenner and Joris van der Hoeven, actually will enable us to tell us more about the actual differential equations that are satisfied by elements of E, but there are a lot of things to deal with still. So I'm just right. Yeah, I also want to say a few more things about if you have an element that satisfies an algebraic differential equation like that there, that it is not, that is bounded by some iterated exp, right? That is also a part of a very general result, which I want to just mention for your information. Oh yeah, I should also mention that in connection with this Pfaffian business, there is this paper by Blaise, Moussu and Sans, solution non oscillante d'une équation différentielle et cours de Hardy in the journal, the annals, the Annales of the Institut Fourier, 2007, where they have also very interesting extension theorems about Hardy fields, which are related to the theorem in the beginning of this section, right, where y double is in the real where you assume that y double is in the real closure of HY, but okay, I haven't studied that paper yet, but it seems that the difference is that it's more general in the sense that it talks about arbitrary for differential equations of arbitrary order, while what we did here is just about order 2, but the differential equations are all over Q, and in our situation we dealt with differential equations over any Hardy field. So of course it could be that these results in that paper could be extended also to more general Hardy fields. And that would certainly be very interesting anyway. But their work also has to do with this Pfaffian business. Right, so it might certainly be relevant for this kind of question. Okay. Yes, so to finish today, I want to say one more thing about things that satisfy an algebraic differential equation automatically satisfy a certain bound. So no trans exponential germs in E because, well, first of all, every element is differentially algebraic, and we have a very general fact, namely, well, it occurs actually in a somewhat more general setting in an old paper of us by Matthias and me, let H be a Hardy field, but it could occur even earlier in let H be a Hardy field, and let X be an H, which of course is fairly innocuous, and let's have a differential polynomial y prime up to yn. Then you can find an f, then there is an f in H. Actually, yeah, a positive f, such that either py y prime to yn is bigger than 0 for all H-Hardian germs, for all H-Hardian y which are bigger than f. No, bigger than x pen, sorry, x pen f. Yeah. Or p y prime to yn is less than 0 for all H-Hardian y that are bigger than, yeah. So all sufficiently large H-Hardian germs, yeah, sufficiently large measured this way, if bigger than the nth exponential of a certain element in H, if you plug it in P, you will get something that's greater than 0, yeah, or you will always get something that's less than 0. In other words, you never get 0. Yeah. Yeah. So any H-Hardian y with that satisfies this differential equation satisfies y less than or equal to x and f. Okay. Well, of course, this is only significant for positive y, but of course for negative y you have a similar thing. Right. Okay, and so you get this exponential bound that I claimed here. Oh yeah, there it's a bit more special. Namely, I say x and x. So yeah, the f here can, if you look at the proof, you can for certain h's, like you can take just x. Okay, so I think I will stop here and start a new section on Tuesday. Yeah, I have to make a decision about how I want to continue. By the way, this course, when I looked at when this course, how far the course will continue, it seems that there is a stopping date in April. Is that right?
I don't know right now. I'll ask.
Right, because yeah, if it has to stop in April, that yeah, it will make a difference whether what I'm going to do. Right. I mean, there is just a gigantic amount of things that one could talk about. and one has to make a choice that is reasonably attractive for an audience that is not too small. Okay, so let's stop here. Or maybe I should ask for questions before I switch off.
We'll have a question session.
Oh, yeah, okay, right. Well,
Now there's a question.
uh-huh.